Over my past 14 videos, I have explored the world of nuclear war and atomic weapons with the assumption that everyone knows what I'm talking about when I say nuclear weapon. And why wouldn't I? If there is one thing that is truly ubiquitous in the developed world, it is knowledge and consequential fear of nuclear bombs. But despite this societal familiarity, I think it would be a helpful thing to dig a little deeper and try to understand these terrible implements of destruction a bit better. In addition, I will be starting a series on the real-world implications of nuclear war in the 21st century very soon, and I really just want a video I can reference rather than try to stuff a whole technical explanation into each one. And besides, after all of this time, I should probably explain what nukes really are and what they do. This will be my most science-y video yet, and I put a lot of time into fact-checking and researching the stuff I'm about to go over. But as always, I want to remind my dear viewers that I am not a physicist. So if I get anything wrong, or you discover an exception in whatever you see here, please let me know. And since I'm being a bit more candid and off the cuff here, I guess I might as well take the time to say thanks for watching, and please don't forget to subscribe, ring the bell, and check in soon for my new series. With global tensions rising like they are, I don't think you'll want to miss it. Nuclear bombs utilize the energy released from nuclear reactions to create explosions for the purpose of military bombardment. That's the simplest way of thinking about them. But let's get a little bit deeper and a lot smaller. Atoms are the basic particles of chemical elements, and these particles are themselves made up of even smaller particles called protons, neutrons, and electrons. The protons and neutrons make up the nucleus of the atom, while the electrons orbit the nucleus. The number of these subatomic particles in any given element determine what the element actually is. These elements are distinguished by their own atomic numbers, which specifically refer to the number of pronouns found in a given element. Hydrogen, for example, has an atomic number of 1. In addition, each element has different species distinguished by the total number of protons and neutrons. If you have an atom with an atomic number of 1 and no neutrons, you have protium, the most common species of hydrogen. If you have an atom with an atomic number of 1 but that also has 1 neutron, you get deuterium. These species of atoms that each have an atomic number of 1 are referred to as isotopes of hydrogen. This relationship of protons to neutrons also contributes to the stability of a given isotope or nuclide. The nuclei of any given atom is held together by immense amounts of energy, at least when you consider the size of an atom. And when the number of protons and neutrons is equal, that energy is more or less balanced, to put it painfully simply. There are other factors that contribute to the stability of elements, but let's roll with the proton-neutron ratio for now. When this ratio is not close to 1:1, or the atom is otherwise unstable, the atom is said to have excess energy, and that energy has to go somewhere. There are a few ways in which this energy can be dispersed, but all of these processes are referred to as radioactive decay. Hence, any isotope that has an uneven atomic mass is said to be unstable and thus radioactive. Now, I mentioned before that unstable isotopes have to disperse their excess energy somehow, and one of the ways they do that is by violently ejecting particles into other atoms. These ejections can change the nature of whatever element is receiving the new particles, and if those elements become unstable themselves, the process might repeat and create a chain reaction. These sorts of reactions are not all inherently explosive, but in certain cases, when a neutron crashes into an unstable nucleus with enough force, it can cause that atom to split. And remember, I already said that nuclei are held together by immense amounts of energy. See where we're going here? Okay, we're almost there. When atoms start splitting, more neutrons are ejected, which crash into other atoms, perpetuating the process known as nuclear fission. This reaction is inherently messy, as even though the neutron ejection is what concerns us most, other particles are also allowed to fly freely. And back in the early 20th century, nobody knew for sure if such a reaction would stay confined to the test site or create runaway reactions in our atmosphere that could destroy the world. But thankfully, that didn't happen. And that's because fission reactions do eventually fizzle out. And in fact, that was one of the biggest problems the men of the Manhattan Project faced when they built the first atomic bomb. In order to maintain a fission reaction for long enough to make an effective bomb, you need the right materials under the right amount of force at exactly the right time. The materials back in 1945 were uranium-235 and plutonium. Uranium-235 is an isotope of the natural element uranium that is able to sustain a fission reaction, and plutonium is a synthetic element created from the non-fissile uranium-238. Once you have the right amount of whatever element, you have to apply force to it in high enough intensity and at the right speed to initiate a chain reaction. For the Trinity detonation, the material was plutonium, and the force was conventional explosives arranged in a sphere. The explosives would be directed into the core of the bomb, creating a supercriticality, making all of those uranium atoms crash into each other, splitting apart, and releasing a titanic amount of energy. A nuclear explosion. Now, this is a bit of a slapdash explanation, and there is definitely more to it than what I've said here, but that's the way you get a nuclear explosion. Unstable elements are made to crash together with extreme force in nearly an instant, causing the atoms to split, release their energy, and send neutrons careening into other atoms. One atom releases roughly 3.2 times 10 to the negative 11 joules of energy when split, and that's not much. But if you multiply that one atom by a trillion, and then multiply that by another trillion, well then you get a substantial energy release. About 2.92 times 10 to the 13 joules of energy in the case of a 15 kiloton blast. So, 2.92 times 10 to the 13 power joules of energy sounds fancy and academic. And those of you with physics backgrounds probably don't need me to tell you that 29 trillion joules is a lot. But for those of you like me with art degrees, a few examples will help to illustrate the sheer power of atomic weapons. Firstly, there's the classic light bulb example. A 100-watt light bulb uses about 1,000 joules in 10 seconds, which means our 15 kiloton blast produces enough energy to power such a bulb for
9,259 years.
But that's super boring. Here's one for my fellow Americans. One round of God's caliber 45 ACP produces roughly 580 joules of energy. So imagine, my dear countrymen,
50
billion 1911s firing at the same time. Really though, this is probably the most effective demonstration around. Here's what it looks like when 1 ton of TNT explodes. Now 10 tons of TNT. 100 tons of TNT. And at last, 1,000 tons of TNT, otherwise known as 1 kiloton. Now, multiply that last one by 15, and you have a modestly sized nuclear weapon. But even calling 15 kilotons modest might be overstating it, since very soon after the Trinity explosion, the world was treated to the terrifying power of Ivy Mike, the world's first hydrogen bomb, which detonated with a yield of 10 megatons, or 10,000 kilotons. Even before the work at Los Alamos had finished, one scientist in particular was convinced that fission was not the limit for atomic weapons. Edward Teller pioneered the process of nuclear fusion, at least in regard to nuclear weapons, in his quest to build the super. Essentially, the essence of the concept is in the name, in that fusion reactions generate energy by forcefully fusing two atoms together, causing a massive release.
In other words, the parts are heavier than the whole. Why? Because when the fusion takes place, this extra mass or weight is converted to and released as energy.
The process of fusion can be brought about by subjecting elements like deuterium or tritium to extreme temperatures, in the range of about 1.2 billion degrees Kelvin. The need for such high temperatures is what suggests the name thermonuclear, and the use of hydrogen isotopes like deuterium and tritium is where we get the name hydrogen bomb.
Science.
And how can we generate 22 billion degrees Fahrenheit on Earth? Well, with a nuclear bomb, of course.
Of course!
That's right, hydrogen bombs use a fission primary explosion to create the temperatures needed to start a secondary fusion reaction. And just to illustrate the potential power of such a reaction, the Trinity detonation used roughly 140 pounds of plutonium to get a 25 kiloton yield, while a mere 1 pound of deuterium can generate 26 kilotons of energy when fused. With this in mind, and remembering that newer bombs are more efficient, it is easy to see how dangerous a hydrogen bomb can be. There are other processes involved in thermonuclear detonations that increase efficiency and power, but suffice it to say, the implementation of fusion bombs upped the apocalyptic ante to astronomical heights in 1952. While it isn't known for sure how much material was used for Tsar Bomba, it didn't use anywhere close to a ton of deuterium or tritium. And theoretically, there is no true limit to the energy release possible during a thermonuclear explosion. Don't forget, our own sun is powered by nuclear fusion, and scientists have been trying for decades to control fusion reactions for use in power plants. If a fission reaction can power a light bulb for
9,259 years,
imagine how many state-sponsored stasis pods could be perpetuated by a fusion power plant. And just in case you were wondering, a 1 megaton explosion generates roughly 4.184 times 10 to the 15 power joules of energy. That's about 4 quadrillion. And yeah, that's so fantastically huge, it's basically meaningless, but it's still pretty impressive. And for brevity's sake, I'll be using a 1 megaton explosion as our sample size for this next section, which is convenient because roughly 1 megaton is the most common yield for nuclear weapons of today, so pay attention everyone. Now that we know how nuclear bombs work, we have to explore the more important part, what they actually do. Put more succinctly, where does all that energy go? The energy in an atomic bomb is dispensed in 3 principal ways: thermally, kinetically, and radiologically. Roughly 50% of the energy from an airburst nuclear explosion is released kinetically in the form of the initial blast and shockwave. When the detonation occurs, an extraordinary amount of heat is generated, and everything in the vicinity of the weapon, including the components of the weapon itself, is immediately vaporized. And I think I should repeat that again in detail to drive the point home. All materials in close proximity to the bomb are immediately, as in less than a microsecond, vaporized, meaning that rocks, metal, and even freaking dirt is heated to the point that it becomes vaporous. The bomb generates so much heat that the very essence of our planet changes around it. Anyway, back to kinetic energy. In addition to forming brand new gases of its own, a nuclear explosion also superheats any other gases in the vicinity of the reaction, even oxygen. This causes a bubble of hot gas to expand and push against the air around it, thereby creating a pressure wave that compresses the air outward in a ring around the ignition point. The overpressure within a 1 mile radius exerts itself on surrounding objects at 20 pounds per square inch, and the blast wave generates winds at velocities as high as 470 miles per hour, significantly faster than an EF5 tornado. Hey everyone, I'm in the middle of editing and I wanted to record a quick addendum for this section. When I talk about 20 psi of overpressure, I'm not talking about raw force. If you look online, it'll probably tell you that with a 1 megaton explosion, the force exerted within 1 mile of the epicenter is about 100 psi, and that's true. It can actually get even higher than that. But overpressure specifically refers to the amount in psi of atmospheric pressure above normal. And that's huge because that means that 20 psi is being exerted on every single inch of every surface within a mile. The forces that can generate are absolutely massive, and they are more than enough to destroy buildings and snap trees like twigs. So yeah, it's really huge, and I just wanted to make sure that was clear because it kind of sounds like a small amount when you don't know what overpressure actually is. And so for those of you like me who didn't know until starting to do this research, I figured that might be helpful just so we're all clear. Needless to say, any building near the epicenter that isn't vaporized by the thermal radiation will need to withstand outrageous amounts of force. And obviously, windows and doors stand no chance within that 1 mile radius. But even at distances as far away as 5 miles, buildings will be rocked and damaged, and wind speeds will reach as much as 100 miles per hour, as fast as a Category 1 hurricane. The area of possible effect from a 1 megaton bomb is roughly 452 miles, if we assume the damage radius is about 12 miles. Keep in mind, this does not mean that everything within 12 miles is destroyed, only that people, places, and things within that radius could be damaged or otherwise affected. I suppose I should say that the area of effect gets a lot bigger when you consider radioactive fallout, but that's something we're going to get into a little bit later. The next largest energy expenditure during a nuclear detonation is in the form of thermal radiation, or more simply put, heat. It is a widely known fact that when they split those atoms, it's hotter than the sun. But that fact is so widely known that I feel it has lost some of its punch, and that's a shame, because that punch would hurt. A lot. Because thermal radiation is essentially just light, it's the first thing anyone would feel during a nuclear blast. In an instant, thermal radiation from the blast can ignite fires as far away as 5 miles, with anything within that 1 mile radius being subjected to temperatures as high as 10,000 degrees Fahrenheit. In addition to the superheating of gases mentioned before, the heat from the explosion also vaporizes radioactive material from the weapon itself, causing the miasma of vaporized solids to mingle with the fission products. This cloud of fun and happiness is made buoyant by the extreme heat, which causes it to be lofted high into the atmosphere, as high as 70,000 feet, where it can then drift for a period before falling out in a particulate form like ash or even in a liquid form like rain. This tends to happen after about 30 minutes or so, but existing weather conditions can cause earlier fallout and create hot spots near the blast zone. This segues our discussion comfortably into the last major way in which energy is released in a nuclear explosion: ionizing radiation. Now, just like our own sun, a nuclear bomb is classified as a broadband source of light, meaning that it emits light in all frequencies, releasing varying amounts of photons from the entire electromagnetic spectrum. This means radio waves, gamma rays, the thermal radiation we just mentioned, and beyond. In a real sense, this broadband emission is responsible for all of the effects of nuclear weapons. During nuclear fission, those same neutrons that caused the explosion can also collide with living tissue, resulting in severe radiation sickness, tissue damage, and death. Neutron radiation is most intense within a 1 to 2 mile radius from the epicenter, posing a significant threat, but only to those that somehow survive the blast and heat.
Neutron weapon is designed to be used against massive and perhaps overwhelming tank forces.
And though the neutrons diminish in intensity further from the epicenter, they do contribute to nuclear fallout, so that's nice. The other kind of radiation release is in the form of gamma and X-rays, released during the fission and fusion processes and by the succeeding effects of those gamma rays causing electron scattering in the air around the blast. X-rays can be very dangerous, but in the case of a nuclear blast, they are confined to the immediate vicinity of the reaction. And while gamma rays are similarly concentrated within the blast zone, they will also travel miles from the epicenter and pose a significant health risk to anyone within a 5 mile radius. Exposure to gamma rays can cause cellular damage, which can result in cancer, and higher doses can even cause acute radiation syndrome, which can result in an extremely painful, sometimes agonizingly slow death. And it's not just buildings and people that experience cataclysm caused by nuclear weapons. With the incredibly high temperatures and overpressure, the environment itself is also temporarily, or maybe even permanently, warped by nukes.
Nuclear winter, nuclear winter, nuclear winter, nuclear winter, nuclear winter.
Some of the most obvious environmental changes come from the lofting of smoke, ash, and dust into the atmosphere. The bomb itself is capable of injecting millions of tons of material into the sky, but even more pollutants might follow if the detonation causes firestorms to form. And all of this pollution, while not super ideal, would pose no real threat to global environmental stability. However, most scientists conclude that if you had, say, hundreds of such explosions, it would pose an extreme hazard to the global climate. But that's a subject I'm going to be getting into in more detail in my next video.
Nuclear winter.
Finally, I'll mention briefly that nuclear weapons, and that's all nuclear weapons, generate electromagnetic pulses caused by that ionizing radiation I mentioned earlier. When all of those particles become suddenly electrically charged during a nuclear detonation, it can cause electronic devices to overload, short, and ultimately shut down or become otherwise unusable. Electromagnetic pulses are less of an issue with ground bursts and low-altitude air bursts because the effects of the EMPs are limited to the radius of destruction. But they would still cause serious problems with communication for first responders and such. EMPs are especially effective at high altitudes, where the charged particles are able to spread great distances and cause untold electronic devastation. Just in case I'm not getting the point across, one high-altitude nuke detonated over Kansas could shut down power grids across the entire United States, and it could take weeks to restore power once those grids are down.
Man, that sucks! Why?
At this point, I hope I have painted a more detailed picture of exactly what happens during a nuclear explosion, and provided an explanation for how these things occur. What you have at the end is a massive, super hot, super powerful, deadly poisonous explosion that utterly destroys everything within a mile of its epicenter, and drastically affects the area around it within 12 miles. This is not even mentioning things like the effects of nuclear weapons underwater or underground, or even burst height for that matter. There's still a lot more to learn, and if any of you would like to know more, there is a wealth of knowledge on the subject in this book. Though, fair warning, it is super dry. And while it is quite old, it is an authoritative source written by men who not only helped design nuclear weapons, but who also had access to the results of nuclear weapons testing that have not occurred under American auspices since 1992. I'm sure there are many other videos with smarter people than me going way more in depth than I have here. But I hope this explanation has been informative and a little scary too. I hope it serves as a helpful companion to my forthcoming videos and to any other creation of mine that discusses nuclear weapons. If any of you feel like I could have mentioned more, let me know and I might do a follow-up that goes more in depth. But do stay tuned for my next video, as I will be discussing some more specific environmental effects, especially as they pertain to the theory of nuclear winter. Thank you everybody for watching. I don't want to get too far ahead of myself here, but it's looking like I am very close to the point where I'll be able to monetize this channel. And that's really exciting because one of the biggest reasons I haven't been able to put out more videos is because I have to work more. With the kid being here, I gotta work a lot, gotta grind all the time, me and my wife both, so not a lot of time to write and produce videos. But if I were able to monetize the channel, that would give me more of an excuse to devote time to it. So that's something I really want to do, and so it's exciting that could be a possibility pretty soon. Looks like the first thing I'll probably be able to do is open up channel membership, but I don't want to do that until I have something exclusive to offer members. So if you have any ideas about that, let me know. I've got a few things floating around, but nothing concrete just yet. So yeah, exciting times are ahead. So any of you that haven't subscribed, please make sure to do that. Everybody, please like the video, leave a comment, ring the bell, all that good stuff. And yeah, I'll see you in the next one. Thanks a lot. Bye. I always end these videos like I'm leaving a phone message. The thanks a lot, bye thing. You know, I need to not do that as much. I'm not as good off the cuff. You know, I write scripts and I read the scripts. I don't chatter at the camera. You know, like I'm doing right now. Thanks a lot. Bye.